Hey class, many of you have been asking me for some pointers on number 4 on the workshop here, so I thought I'd make a little video giving you some hints. As we read here, we have this supposedly massless rod, which is a joke, but we're going to approximate its mass as being 0. We're told that the rod has a length of 5.7 meters, so I don't know what this thing is, but it's huge. A giant swinging cannonball. We're told that the ball is 4 kilograms. And it's initially held and starts here at this point A, and it's going to, which is 30 degrees above the horizontal, which is labeled here, and it's going to be released, and it's going to then swing around to point B. Now, sometimes people read this, they're like, how's it go from A to B? Because you think A, B, C, D, but no, it's actually going to swing down because of gravity through D, then C, and then up to B. So it's a little confusing in terms of the order, but the first thing I ask you to solve is from A to B, and so that's why, well, actually, I guess from A to C, but it's moving towards B. Anyway, the picture is probably not the most perfectly labeled, but that's what's happening. So that's what we're told. We're really not given any other information, and we're asked to figure out what is the speed, so the linear velocity at point C. So for, again, considering the ball when it's right here at point C, it's going to, at least for the initial time, be moving up this way, and then on the way back down it'll be moving in this direction, but we're only going to consider that first one. What is this linear speed here when it's at point C moving in this direction? And so I think a lot of you, because we're just learning about all this rotational stuff, your first thoughts are to try to figure out something about rotational acceleration, or angular acceleration, what's alpha, what's omega, what are these different variables, but we aren't given much, right? We have gravity that's pulling down on it, but even that is super tricky, right? Because gravity is pulling straight down all the time. At any different point, gravity is straight down. And so the acceleration of this thing, the angular acceleration and the linear acceleration, is going to be constantly changing. At each point, it's going to have a different angular acceleration. So all of our equations of motion, they don't work because we don't have constant angular acceleration. So in fact, the kind of pro tip on this problem, to get started, we need to instead think about using conservation of energy. So in some ways, this problem is actually thrown on here to kind of be a review or a trick question to get you ready for the upcoming celebration of knowledge, so that you can get practice identifying different ways of solving these problems. You get stuck in one route, you need to try a different tool from the different tools you have in your tool belt. So let's instead think of conservation of energy, meaning that our energy at point A plus any work done by outside forces will be equal to our total net energy at point C. And in this case, there's no outside forces because we're ignoring air resistance and so on, so the net work outside is 0. At point A, it's stationary. There's no springs, so the only energy it has at point A is mgh. All right, now what is h for a second? Well, okay, let's think about this. First, let's erase some of these. Oh boy, that's erasing my picture. That was close. Okay, let's try doing this one. There we go. All right, so let's start and think about h. Well, we need to define a 0 point. You may think that it's beneficial, and you may choose to define 0 here, which you can do and you'll need to do for part B. But what I'm going to do is I'm going to go ahead and let's just call point C's elevation 0 initially to make our life a little bit easier. So this initial h, which maybe we'll call it HA, the height for part A, is labeled there. So HA, okay. And then that equals, at point C now, since we're calling that 0, the only form of energy it's going to have is kinetic energy, 1/2 mv squared. And so if we want to find the speed there, we can just solve. Cross out our m's. V is just going to be equal to the square root of 2gha. Ha! See, HA, ha. Okay, anyway, the question then is, well, what is HA? How can we figure that out? Well, good question. Let's see. HA is going to be basically this, oh boy howdy, not the highlighter again. All right, let's try that again. It's going to be this distance plus this distance. And I chose those two to represent HA because I have these little triangles with the radius as my hypotenuse in both cases, the angle 30 degrees in both cases, and HA then is just going to be equal to 2 times this length, which is going to be the radius times the sine of 30 degrees. Check it out though, this is really quite nifty. I don't know if you know off the top of your head, but you could check it on your calculator. Sine of 30 is just 1/2, 0.5. So HA is just going to be 2 times R times 1/2. 2 times 1/2 is 1. HA is just R. Ha. So then you can plug that in over here and solve for V. All right, that's nifty. Pretty exciting, pretty fun. What about part B? Part B does not ask us for the speed at D. Instead, it asks us for the tension in the rod at point D. And we might need the speed for it, we'll see. But we're asked to find the tension at point D. So let's go ahead and kind of clear up our picture here. All right, so we're looking at point D. Tension right away. First thing, what do you think? Oh, it's a force. Anytime we're dealing with forces, we should think free body diagram. So if we come over here, we're looking at point D. Maybe you label it D. At point D, what's the free body diagram going to look like? Well, it's going to have the weight going down. It's going to have that tension in the rod going up. And we know that the net acceleration, a centripetal acceleration, must be up because you always need that inward pointing acceleration for something going through circular motion. And that's all. It has inertia carrying it through and so on, but we don't need to worry about any of that. This is all we need to worry about. So if that's the case, then we can do sum of our forces in the y direction equals ma. Switch to blue here since we're on part B. So, oh boy howdy. So what do we got? We got tension going up minus weight going down equals m times centripetal acceleration. Okay, we want the force of tension. Well, it's just going to be equal to mg plus m times centripetal acceleration. And just as a side note, we know centripetal acceleration is v squared over r. So m v squared over r. Now we just need to find v, but this here is v down here at point D. Well, guess what? We can do the same game. Conservation of energy from A to D. So if we do conservation of energy, EA is going to equal ED. At point A, it's still going to be mg h, maybe we'll call it h2 or something. I called the first one HA. That's a bad name probably because that's really the height between point A and C. So maybe we'll call this one instead of h2. We'll go stick with the same format and call this one HAD, the distance between those two. Well, this guy we're going to have to find, obviously, but we know that's going to be equal to 1/2 mvd squared. And so continuing on, I'm going to just scroll down here for a second. Our m's will cancel, and vd, just like we saw before, is just going to be equal to the square root of 2gh between a and d. So now we need to figure out what that is. We found HAC here as being just r. This new one, though, is going to be this distance from here all the way down. But if you notice, that's just r plus r sine 30. So HAD is just going to be equal to r plus r sine 30. Again, it's this plus this. And we already decided sine 30 is 1/2. So HAD is just going to be 1.5 or 3/2 r. That's cool. So you can plug that in to solve for V. Once you get this number for V, pop it in here, and you get the tension in the rod. And that solves this problem. Boy howdy, oh yeah, physics rules, so much fun, box worthy, yes. All right, so let me know if you have any other questions. Have a box worthy day.